So we're not done talking about transformation with matrices. However, let's kind of review some of the things that we've talked about already. So the first concept we reviewed or we talked about was dilation, where we use a scalar multiple that we just multiply our entire original or pre-image matrices or matrix that refers to a particular polygon. By the way, I've only been using a triangle just because it's easy. I could also have used a quadrilateral or a larger figure, or I could also use 2 points, which refers to a vector, to kind of refer to that, but we can talk about that at a later time. All right, so at this point, we see that we've got the dilation way of creating a transformation. We could also have to translate, we can also do what we did or what we talked about before, adding or subtracting some value, let's call it A, to each of the X values, and then and I'm going to say adding some B value to the Y value in order to translate it to the right A and up B, or depending on if A and B are positive, right up or left down. Okay, so now that we've gotten through that, let's talk about other ways of transforming. We're going to talk about 3 ways, and I'd like you to copy this down because I'm not sure if you've seen it before. So let's go ahead and start with a new triangle labeled ABC, and then we're going to deal with this in a minute. We'll talk about what these different matrices can do. And so let's go ahead and give a matrix that represents that polygon. And so here we have that matrix right here. All right. And so now we're going to talk about what we can do. I'm going to erase the ABC. That's just to show you the coordinates. We're going to talk about what we can do to change this. Now, you guys remember we talked about the identity matrix, right? So if I take the identity matrix and I multiply it, right? The identity matrix has these, let me move everything over. Hold on. Okay, there we go. So if we were to multiply this matrix if we were to multiply these matrices together, recognizing that this is the identity matrix, what do you expect would happen? Well, I'd multiply 1 times 0. Not 1 times 0, 1 and 0 times 2 times this 0 here, and then that would be my first coordinate point. And eventually, if I were to do the whole thing and use the matrix multiplication way, I would end up with, I don't know why this is here. Because this is legit a -2. My bad. I'm like going to totally erase that. Hold on. Let me fix it. All right. My bad. I end up with, as the identity matrix gives us, the same thing back. Now, what I want you to observe is that all of these matrices here do something special. Actually, they're reflection matrices. And I want you to think about, for a second, how multiplying by this guy instead of this guy would change our matrix. So how does that work out? So I'm going to do that. Let's do that, and then we'll see what we'll name each of these different matrices and what reflection they actually cause on our pre-image. So I've rewritten this matrix here. I'm going to multiply, and let's see what we get. 1 times that -2. I'm going to end up with a -2 back there. 1 times, I hope you know what I'm doing. I'm multiplying across this way and down this way and adding the results together and then getting this, right? So 1 times -2, 0 times 0, added up, I get that. 1 times 0, and then 0 times 4, I'm going to get a 0 here. 1 times 3, and then 0 times 1, I'm going to get a 3 here. Notice nothing changed at the top. Similarly, this is the same as the identity matrix, so nothing should change at the top. What do you think is going to happen down here? Let's check it out. I know you're excited. So I get 0 here, 0 here, another 0. This is getting boring, isn't it? Oh, there it is. Whoop, there it is. There's a change. And then over here I get a -1. Yeah? So let's see what this new, so if this is A, B, and C, this would refer to, I guess, A prime, B prime, C prime, if we're thinking about it in terms of translating, right? So I can look at that. Let's see what I get when I plug these guys in. Well, that's exactly the same. And 0, -4 is now different. I think my 4 is down here a little too low, but that's all right. And then 3, -1. Say what? Anybody impressed? Can you tell me what we have? A reflection over the x-axis. Yeah, didn't want me to sing, but I did it anyway. Boom. So we have a reflection over the x-axis when we use this particular matrix. So that's what this matrix does. So each of these matrices has a particular thing that they do. Do you want to guess? Do you want to guess what's going to happen when we do it with each? If I were to multiply with this guy, do you want me to do it for you? How about I just give you the answer? It is this guy. Uh-oh, it just gave me a hint of it. Let me see if I can erase and get it. Hold on one more time. supposed to be more like a reveal. Okay, so this is going to give me a reflection over the y. Let's look at it. Let's try it. All right, so what I'm looking at here is I'm like, oh, this is really a lot like the identity matrix, except there's a change in sign here. So it looks like I'm going to change my x value, the sign of my x value from, if it's positive, it's negative, negative would be positive, right? Positive, negative, negative, positive. The y will stay the same, so whatever the y values will stay the same, and we'll get this switch. The reason why I'm thinking about that is I just want you to be able to kind of intuit what would occur if we had this, and we know that the answer is the translation in the y-axis. So when I multiply, I get this, just as I anticipated, it's only a change in sign for my x values, and when I plot these points, I get this blue image right here. And so what I want you to see is that the black image compared to the blue image is a reflection over the x-axis. So I'm going to allow you the fun of trying these next few while revealing what they should do. So this guy should give us a reflection in the origin. So that's kind of like a double reflection, of reflection over y and a reflection over x. Sometimes that looks like a rotation. And this one should give us a reflection. Let me see if I can get it to work. A reflection over the y equals x line is what it says there. So we talked about reflecting over the y equals x line when we talked about inverse functions. They have their reflection is over the y equals x line, and you'll see the same thing will happen if you take an image matrix and you multiply it by this matrix, which is going to be the y equals x, the reflection over x, y line. But what happens when we reflect over x, y? What switches? The x value and the y value. And you notice here, that's what's going to happen if you compare it to the identity matrix. All right, let's go on and talk about a different topic. So in case you were bored with solving matrices, not matrices, but solving systems of linear equations in the myriad of ways that we already are able to, now we have another way. All right, so let's go over the ways that we know. We know that we can do the most frustrating, which is graphing. And the reason why I say it's frustrating is just particularly if you have an answer that's like a decimal. Definitely a decimal in the 10th place would be hard enough on a regular grid, but you know, in the hundredths place or anything like that would just be nearly impossible to get an exact answer. We also have substitution, which allows us to use our algebra skills, but even in a more effective and efficient way, we can use our algebra skills, perform elimination to solve our systems of linear equations. We recently talked about ways to solve systems of linear equations, and there were two that we talked about so far. We talked about Cramer's rule, which everyone loved. We talked about Cramer's rule, which allowed us to use determinants to solve. We also talked about augmented matrices and doing row echelon reduction. Do you guys remember that? We had a couple rules. Basically, you could add and subtract the two rows to, yeah. So I'm going to put augmented matrices here, augmented matrices. Okay, so we had that. So now we're going to actually figure out or talk about using inverted matrices. So it'll go in our matrix toolbox, our matrices toolbox to solve these systems. Let's get started. Let's start off with this problem, and we're going to talk about how we're going to write this in a different way considering matrices. So we're not actually going to do the augmented matrix way. We're going to write this as the product of the matrix 2, 3, -1, -1. Notice I'm just using the coefficients there. And I'm going to multiply it by the, I don't know, I've heard it called column vector, or this matrix is this matrix xy, and it should equal this matrix -1, -1. All right, this column matrix. So let's kind of think about what this means. If I do that multiplication, let's go ahead and do it. I don't think we practice it as much as I would like to have practiced it. If I were to multiply these guys together, it would mean that I would take, I don't know what shape this is, let me take that away. It would mean that I am multiplying 2, 3 times xy and then adding them together to get the first column, right? To get that first value. So 2 times, I said 2, 3, 2 times x is going to give me 2x. 3 times y will give me plus 3y. And okay, it should equal -1 over 1 over -1 when I'm done. Well, yeah, that's exactly a restatement of this. And similarly, if I multiply -1 times xy, this row by this column, I will get -x plus a negative y, which is that, should equal this. And therefore, this element in the matrix should equal this one, and this one should equal this one. So you can see that this is just a restatement of our problem. So let's see if we can think through a way to solve this. So the logic behind using inverted matrices is to think about how I can get xy alone, because my goal is to solve for xy. And so I'd really like xy to be by itself. And though we don't have division per se, like, because I think our knee-jerk reaction would be divide both sides by the other matrix. We don't have division per se as a tool in when we do with matrices. We can multiply, and so it would be really cool if I call this matrix A, right? And I'll call this matrix B, and this matrix C, right? And I know if I multiply these two together, I get this guy. If I were to multiply this matrix by its inverse, right? We remember that we have inverse matrices. And if I do it to one side, I've got to do it to the other. Multiply that matrix by the inverse. And notice the order does matter, so I've got to be really careful how I do it. I can't multiply by the inverse matrix of A on the other side. Stay with me. If I do that, I'm going to get the identity matrix over here, right? Yeah, I'll get the identity matrix over here times B would be equal to C. And since this is just the identity matrix, this is just going to be B is equal to, why not times C? B is going to be equal to A inverse C. So it's really cool if we can find the inverse value of A, the inverse function, not the inverse function, the inverse matrix of A, and now we can get started. So let's go and do that. Okay, so we got to find that inverse matrix. So we need to do this. To do it, we need to find the determinant of matrix A. I don't think those lines are necessary. The determinant of matrix A, 1 over the determinant of matrix A, times this little funky matrix, which comes from switching the place of these two on the diagonal. So instead of 2, -1, it's going to be -1, 2. And then just changing the signs of these guys. So once I do that, this is called the adjugate matrix. All right, so once we do that, we're going to get our answer. We remember how to find the determinant, so let's do it. Okay, so we'll start here where we're going to work out the determinant, and we see that we get 1. How convenient. And so our inverse matrix of A happens to be the same as that adjugate matrix. So now we've got this. We're going to go back to our original problem and solve for x and y. So you guys remember what we talked about. So what we need to do is multiply. If we were to multiply both sides by the inverse matrix, we recognize that we would get B alone, which is our XY matrix, and all we'd have to do is multiply it by the C matrix, obviously maintaining order in the way that we talked about before, and we'd have our answer. So we're going to do that right now. Let me rewrite this. So there we have B is equal to A inverse times C rewritten out. So nothing to do on this side, but we definitely have a little bit to work on over here. So I know that XY will equal the following. I'm going to multiply this guy by this guy and get my first element at the top, this guy by this guy and get and get the second element at the bottom. So that yields a 4 here, and then over here 1 times that's going to give me -1, and I get a -3 here. Exactly the 2 numbers that I came up with before. So x is equal to 4 and y is equal to -3. I know that that did not seem as much fun as you wanted it to be, but it's a method that we need to know, and it works, and that always feels good. So you have 6, count them, 6 methods to solve linear systems of equations. You could not be the most impressed, right? Okay, fine. All right, one more video and we'll be done the cleanup session. We'll start some new stuff.